Neutron Controls introduces our first release of an application-specific development product line called the REDLINE ToGo Kit. The first application in the ToGo Kit family is BLDC motor control, featuring redundant motor control. This application kit is made from our established a la carte REDLINE Flex Kit product line and includes 2 BLDC motors plus open source application software. To ensure success out of the box, the kit is fully tested with the provided motors. Our open source application is a capable teaser application which allows complete visibility into the implementation details, thus providing a solid start for your custom application. It is important to note that every motor type has its own characteristics. Part of your development journey will be to modify the configuration and software to match the target motors you intend to use. This video is focused on operation in redundant mode, which is the primary application feature. Our REDLINE products are designed around the powerful Infineon Oryx processors and for highly efficient software development accompanied by the tasking development toolset. Neutron Controls is a recognized solution partner of both Infineon and tasking, so you can be sure that Neutron Controls has strong relationships that can be leveraged to ensure your success. On the left screen, the BLDC kit uses the REDLINE Flex Kit TC297 MCU processor module mounted on the base carrier, with 2 BLDC motor control interface modules and the power interface module connected to the base carrier. The computer is connected to the kit with the Infineon DAP Mini Wiggler, and the computer terminal display is on the right. We will now power up the kit. The board comes alive featuring a substantial amount of status LEDs while the terminal scrolls through the startup sequence. The detail of the terminal log and the LED definitions are beyond the scope of this demonstration. However, our documentation suite provides the user with the necessary information. The open source BLDC software has a number of commands. Every command is issued by starting with BLDC, followed by the command and arguments. A foundational command is the getStats command, which returns the status for the specified motor. In this case, the getStats command is consecutively issued for each motor, and we can see that both motors are in standby status, which means the motors are in independent control mode. Both are stopped and waiting for a command. For this demonstration, the kit needs to be switched into redundant mode. The setRed command is issued followed by consecutively issuing the getStats command for each motor. As you can see, the status of motor 1, the primary motor, is in standby, and motor 2 is now in redundant status. Redundant status means motor 2 is stopped and waiting for system commands. I say waiting for system commands to distinguish commands issued by the user from the terminal. The pattern of issuing a command followed by a getStats command for each motor will be used throughout this demonstration. The first demonstration will be a single fault scenario implemented by an interruption of electrical power to the primary motor. In redundant mode, the kit is designed to use Motor Control Module 1 as the logical controller for both Motor 1 and Motor 2. Of course, Motor 2 remains electrically connected to the Motor Control Module 2, and as such, the role of Module 2 is to listen for commands for Motor 2 from the system and pass on Hall effect sensor information to the system. User commands and motor speed control via the onboard potentiometer are effectively disabled for Motor Control Module 2. We start Motor 1 by issuing the start command. Motor 1 starts turning immediately in the counterclockwise direction. The terminal shows that motor 1 is running and that motor 2 remains in redundant status. The CCU6 provides the motor starting segment and the next segment in hexadecimal format, as read from the hall sensor of motor 1. The user can use the onboard potentiometer of module 1 to change the speed of motor 1. As the user turns the pot to the right, or counterclockwise, the motor speed reduces, and to the left, or clockwise, the speed increases. You may observe that motor speed appears to be changing erratically, or even changing direction. This is not the case, but is simply the interaction of the lighting and camera resulting in an undesirable strobe effect. Next, an electrical fault is introduced on motor 1 by a user depressing the module 1 onboard push button. The button is depressed and immediately motor 1 slows while motor 2 starts. On module 1, the green fault status LED to the right, indicated by the arrow, comes on. Simultaneously, the push button illuminates. Meanwhile, the terminal displays a fault captured by the CCU6. The software notes it is a single fault. The CCU provides the hall sensor reading and the software issues the command to start motor 2. Issuing the getStats command displays that motor 1 is faulted and motor 2 is running, which agrees with our observation of the kit. When in redundant mode under a single fault condition, the user demonstrates that module 2 does not control the speed of motor 2. The user turns the onboard pot of module 2 both clockwise and counterclockwise to demonstrate that the speed of motor 2 does not change. When the user adjusts the pot on module 1, we observe that the speed of motor 2 does change, thus demonstrating the logical condition that motor 2 has effectively replaced motor 1. To further demonstrate this logical control state, the user issues the stop command to motor control board 2, resulting in a failure response. The status, as expected, is that motor 1 is in a faulted state and motor 2 is still reported as running, confirming that indeed the command failed. Since motor 2 is logically under the control of module 1 as a logical replacement for motor 1, the command to stop motor 2 must be issued through module 1 by setting the command argument to motor 1. The user proceeds to issue the stop command to motor 1 and we observe that motor 2 now stops. Note that the LEDs which gave a visual representation that motor 1 was faulted are now extinguished. This means the fault condition has been cleared and the getStats command confirms that motor 1 is back in standby state and motor 2 is once again in a redundant state. The second scenario demonstrates a double fault where one of the faults is due to a physical motor jam. It is possible for the primary motor to incur a fault, causing a switch to the redundant motor, and before the first fault condition can be resolved, a second fault on the redundant motor occurs. This situation will be demonstrated, including the final resolution. To start, we make sure the motors are in redundant mode, not faulted, and at rest. Specifically, the state for motor 1 needs to be standby, and the state for motor 2 needs to be redundant, and this is confirmed in the terminal. As before, we start motor 1 followed by the getStats commands, confirming that the system knows motor 1 is running and motor 2 is ready to take over should motor 1 experience a fault. Previously, an electrical fault was implemented on motor 1 with the module 1 push button switch. This time, the user will emulate a physical failure by jamming the rotor of motor 1 with a pair of pliers. Immediately after the rotor is jammed, module 1 fault LEDs are illuminated and the terminal displays that the CCU6 has received a motor 1 trap. The software reports it is a single fault. The CCU6 provides the segment at which the motor 2 starts, and the software reports that the start was successful. Also, we saw that motor 2 started immediately, and issuing the getStats command confirms that the software reports the correct state for each motor. Now, a second fault will be introduced on motor 2 using an electrical interruption of power. It should be noted that Module 2 is subordinate to Module 1 under normal redundant control. However, Motor 2 is connected and gets electrical power from Module 2. So, the convenient way to interrupt power on Motor 2 is to use the onboard push-button switch of Module 2. The button on Module 2 is depressed and immediately Motor 2 comes to a stop. The fault LEDs on Module 2 are illuminated. The terminal displays that the CCU6 received a trap due to the Motor 2 failure. The software reports that Motor 1 and Motor 2 are faulted, which is reported as a double fault. The getStats command confirms that both motors are faulted. The illumination of the fault LEDs on both modules provides the visual representation of the states of the motors. So now we have a situation with both motors stopped due to faults. In practice, it is very possible manual intervention is needed to correct the situation and get the motors running again unless the faults were due to a temporary condition such as a momentary excess load on the rotor or an electrical brownout. In this case, one can try to clear the fault states and then restart the motor. Although motors are not running, the stop motor command has two functions. One is to stop the motor, but the other is to clear the fault state. The stop command is issued to Module 2, which results in a failure response because the system is still in redundant mode and both motors are under the logical control of Module 1. When the stop command is issued through Module 1 with the argument set to Motor 1, the fault LEDs are extinguished on both modules with Module 2 leading Module 1. Issuing the getStats command displays that the motor states are as we expect for motors that are at rest and in redundant mode, confirming that the fault state on both motors were cleared. At this point, starting Motor 1 could be attempted to see if the physical condition which caused the fault is no longer present. Otherwise, the fault will be raised again. Since we forced the fault, we know it was cleared, and we will conclude this demonstration by returning the system to independent motor control mode. When issuing the setRed command with the off argument, the system is taken out of redundant mode. This is confirmed by issuing the getStats command to each motor. Both motors are now in standby state, ready to be controlled independently by each of the respective motor control modules. We want to thank you for watching this video and would like your feedback. We are interested whether this video was valuable to you, any suggestions for improvement, and requests for videos on other topics. Our REDLINE development kits are designed to accelerate your development projects by providing both application-specific REDLINE ToGo kits and highly extensible REDLINE Flex kits. Our REDLINE products allow you to skip custom prototyping and provide a fast path to proof of concept. Neutron's Controls is very open to early, non-committal discussion on your development projects and challenges, so contact us and open a discussion.